start the movie recording, and then we'll go to where we want to be. Okay, so because we're recording it, I'm going to be doing strange things like repeating questions so that they get picked up by the microphone. All right, so today I want to start with some syllabus stuff, and then we'll get kind of into it, what I call my physical metallurgy rules of thumb. Why isn't this advancing? View, slideshow. There we go. Okay. So the full syllabus is up on Carmen. Everyone can get to the. Does anyone not have access to the Canvas site? Carmen? Okay. So everything will be up there. Everything is going to be grouped by modules, right? So whatever section we're in. So the notes for a particular section, the reading for that particular section will all be together. We do meet here Monday, Wednesday, and Friday, 8 to 8:55. My office hours are going to be Monday from 1 to 3 in the afternoon. That was a time that didn't seem to conflict with any other core classes, so it should be a pretty open time. If you can't make those hours, just let me know and we can always set up a different time. Ben, the course TA, is also up here. I want to stand up. Yeah, it's just GEORGIN, right?
Alright, so my name's Ben. I'll be TAing this course, mostly just doing grading and stuff. I'm a student under Hume-Rothery's group, and my research focus is nickel and titanium-based superalloys, so it's kind of related to this stuff. My office is at CMAS, so I don't know how often you guys are able to go down there or what. So my office hours are going to be mostly by appointment, and then before the midterms and the finals, I'm going to set up like a class study or something. It'll be on campus, but that'll be to be determined.
So either you got two sets of resources, either me or Ben are more than happy to spend the time and help. So the objectives for this course, right, is basically alloy design, right? What are the guiding principles behind alloy design? And that's sort of the long-range goal, but to get there, we have to understand a lot of other stuff, right? And this is really has a lot to do with the effect of alloying elements on phase stability, morphology, transformation kinetics, and properties, right? Most of the time we're going to be concerned with mechanical properties. But in other cases, such as transformer steels, right, we're going to be interested in the electromagnetic properties. We want to hit all the major classes of ferrous and non-ferrous alloys. The history of this course is originally there were 2 quarter-long courses. One was non-ferrous metallurgy and one was ferrous metallurgy. When we went to semesters, those 2 got combined into one. But because Professor Fraser was teaching it, it was non-ferrous metallurgy with like a week of steel at the end. I'm trying to rearrange that a little bit and sort of go more by tonnage and actual use, right? So we're going to spend a bit more time on steel and aluminum because those are the important alloys, and that's where most of our graduates who don't go on to graduate school end up working, right? And people who do metallurgy research, that's where most people are. Then, of course, we are still going to spend a significant amount of time in the second half of the semester on titanium, nickel superalloys, copper, brasses. Right, and then we really want to the key idea here is processing structure and property relations in these alloys. This is just a list of the specific topics. I've added a couple things. Really want to break out what I call the structure of metals. And this is what we'll be doing basically for the first week. And then I'm adding some things at the end on metallic glasses and high entropy alloys, and a little bit more on the deformation processing, thermomechanical processing of these alloys, because it's not just thermal processing. It's not just annealing. It's really the combined processing that's really important. So the grade schema is going to look like this. Because it's an 8 o'clock class, I think people should get credit for being here. Right? It's not easy to be here this early in the morning. So we will be taking attendance on Monday and Wednesday. On Friday, we'll have a short quiz that will be count as attendance. So the quizzes are, I will not be assigning specific homework, right? You guys are seniors and graduate students. I shouldn't be necessarily be having to do that. That wasn't quite correct English. I should not have to do that. What I will do is occasionally on Carmen post some recommended questions and things that you should have a look at that will be highly representative of what is on the quizzes. The quizzes will also be highly representative of what's on the exams. Right? My goal with exams is not to be difficult, but for the couple graduate students who had my mechanical behavior course, that doesn't always work out exactly as I planned. But I plan for the exams to be fairly straightforward. They will be open-ended writing questions, so good old-fashioned blue book exams, and the three of them each count for 25%, and they're not cumulative. Right? We're only testing on the material in each section. So the quizzes will be closed book and notes, and we're going to drop two of the Friday quizzes. Right? Everyone can have bad days. Right? And again, I don't expect you to be superhuman and make it to every lecture. So three lectures will be excused. 3 absences will be excused automatically. And I know for a fact there's going to have to be 1 or 2 that I'm going to have to miss. So it's not fair to hold me to a different standard than you guys. On the ones that I do have to miss, I will be pre-recording the lecture material. Right? So we won't be skipping content. All of the lectures, the ones that I'm recording in class and the ones that I'm pre-recording, are going to be posted on my YouTube channel, and links to that will be each lecture will be on the Carmen website. Right. Oh, and then for exams, a single handwritten sheet for any information you feel is important that you want to write down. We'll talk more about it when the exam comes, but the exams are about key concepts, right? So understanding what's in an equation is more important than being able to write out specifically, right? So for example, when I get to some of my rules of thumb ideas, I'll talk about that a little bit more. Okay, so here's what I'm assuming you already know. So if some of this seems surprising, I really want to know, right? So I sort of expect you guys to know how to be able to read a phase diagram and apply the lever rule, right? Hopefully that doesn't shock anybody. Some very basic fundamentals of solid-state thermodynamics, right? Gibbs free energy, the Maxwell relations. Gibbs-Thomson is very important, right? Who here feels they have a good handle on what the Gibbs-Thomson effect is? Who here feels they have any idea of what the Gibbs-Thomson? Yeah, Alejandro. Yeah. Just since you're the. Well, yeah. So the free energy, the bulk free energy, is a function of the surface curvature, right? Right. Really, I mean, like that's the kind of level. I have Clausius Duhem here because I think it's really important, but you may or may not have seen this, and if not, we'll talk about it. Does that ring a bell to anybody? Did Professor Anderson talk about that in the mechanical behavior course? Well, it's a mechanics, it's a solid mechanics way of writing the second law of thermodynamics. That basically says it has to do with entropy production rates, and says that when you deform a material, you should not violate the second law, right? That your energy, your dissipation by all sources has to be greater than zero, right? You don't have things like perpetual motion or heating up a metal doesn't cause it to do useful work, right, by it in and of itself, in a mechanic sense. So some very basic principles of solid-liquid and solid-solid phase transformations. Right, we're going to be reviewing some of this again, but everyone is basically familiar with JMAC, right? And basically familiar with the concept of nucleation by thermal fluctuations in a critical nuclei radius. In terms of mechanics, right, some key ideas of anisotropic elasticity. Right, these are crystals, and so the elastic moduli are not the same along each crystallographic direction. And that plasticity in metals occurs basically by dislocation slip. So you have to know what the slip planes are and the slip directions. Right, that the dislocations are going to move along. Some basic fundamentals of dislocation theory: what the Berger's vector is, what the line direction with screw and edge type is, what the stress field around a dislocation sort of looks like, and we'll talk about that a bit more. And then some basic metallography and materials characterization ideas. Right, so if this list seems daunting and scary, let me know. We can talk. Maybe as things come up in class, let me know and we can do some basic revision. Okay, so I want to sort of have a little bit of discussion. We've got 40 minutes. So I've got two sort of topics I want to take a quick look at and see if we can tease something out as a class, and then I'll move into what I call these rule of thumbs. So everyone signed up for a course that has the words physical metallurgy in the title, right? So what do we mean by physical metallurgy? Right? What are the key ideas? Let me take a slight step back. What's the fraction of grad students that we have in here? Right? So all the grads. Wow, that's higher than I thought. Okay. And then so the undergrads. Okay, so the undergrads, how many of you plan on going on to grad school? That's sort of what I thought. So from teaching the physical metallurgy lab before, my observation that we had people in the metallurgy sort of focus in the department as undergrads tend to leave for those high-paying jobs rather than the $1,800 a month grad school stipends, which is in my mind pretty awesome that a huge fraction of our grads are able to get good jobs right out of, unlike in some other focuses where you really need the extra grad school time. So those of you who are going into are not planning on grad school, how many have jobs lined up? Anybody? So a decent portion. So those of you that do, what areas are you? Steel? Metals in general? Okay. So what's that? Okay. Right. So all areas where this understanding something about what's going on in metals is really key. Right? So how does that tie into this idea of physical metallurgy, right? What separates the idea of physical metallurgy from working with metals, right? What separates this from blacksmithing? Right? When did physical metallurgy become an actual discipline rather than a craft? Right? Or a trade, let's say. Right? What separates a really good welder knows a lot about a huge range of metals. That's distinct from this idea of physical metallurgy. So what is that distinction? Right? And why is this a class? Okay, so there is let's write some ideas down, right? So you would say there's a material design aspect, right, or an alloy design. Okay, this could potentially be part of it. Throw out other ideas. Yeah. So how can we write that in a slightly more general way? Right? So it's not necessarily phase diagrams by itself, but we can say so engineering abstraction. Okay, so practical versus theory. Who said that? I'm going to learn everybody's name. So actually, so before, so what's your name? Alex. And who said Kevin and Ian. Okay. Ian, Linda. Okay. By the end of the term, I promise. Okay, so you said practical versus theory. So can you expound on that a little bit? Who uses practical knowledge? Who uses theory? Who uses both?
I guess like someone will have to use more practical knowledge, whereas like physical metallurgy uses more theory. Like you can figure something out without actually doing it. Or like what should happen.
Okay, so we can say let me change that slightly different to prediction versus reaction. So we want to be predictive in terms of physical metallurgy. Anyone have an idea as to, at least in my mind, there was one insanely important event that without we would not have physical metallurgy as a discipline? Well, yeah, but that was still at that point definitely a craft, right? There was magic pixie dust there. And your name? Dylan. Well, okay, so individual failure events led to individual discussions. Yeah? Yeah, so age hardening in aluminum, important phenomena, but we were arguably doing things before that. Alejandro. Microscopy, right? The invention of the microscope, right? So, characterization, right? So I'll put a big box around that. Characterization. Right. So, in my opinion, the advent of microscopy is the key defining moment of what begins to separate metallurgy as a craft and a trade versus what separates metallurgy as a physical science. Right? So, what's the big ideas behind material science? Right? What defines our discipline? Structure, property, processing, right? So we have our triangle. Right. So the key idea that defines all of Oh, sorry. Right. So the key concept of material science, right, is this, right? So does anyone want to try and put these couple of ideas together to form a cogent, coherent definition? Do I have to call on somebody to put these couple of ideas together? I'll pick on Alex because he's my student. And he was dozing off, so. I said, could you put these ideas together into a simple, coherent, and cogent definition?
Yes, it's understanding the structure and properties in order to optimize processing.
Yeah, but that's yeah.
It's the idea that your properties are going to be determined by your processing and your structure. And as material scientists, we now have those two dictate properties.
Yeah, right. So it's I would argue that physical metallurgy, right, is understanding the structure, processing, property relationships of metals in a predictive way, using characterization and basic physical understanding, basic solid state physics, in order to do so. Right? Physical metallurgy is not just making a series of 100 alloys and testing them and deciding which one is the best. Right? What would separate out the physical metallurgist is deciding, using a little bit of engineering intuition, some basic thermodynamics, and a couple key measurements to make a series of 5 or 6 alloys to determine what's best and be able to a priori eliminate the good bulk of them beforehand, right? And the same goes for processing, right? We don't need to test 100 different heat treatments, right? If we understand how diffusivities and mobilities change with temperature, right? If we understand that BCC metals are going to recover significantly faster than some FCC metals because of the ease of cross slip, right? We know we understand the effect of stacking fault energy on dynamic recrystallization. We can predict and develop processing routes without needing to try them all, right? The space of potential alloys is astronomical, right? The space of alloys and processing is essentially infinite. So how do we search in this infinite dimensional space in a smart way? And that, I would argue, is the key aspect of what we call physical metallurgy. Okay, so why metals? Right? We're in a material science department. We're in one of the few material science departments in the country that has a very strong physical metallurgy program. Right? We're in the only material science department that's home to an accredited welding engineering program. Why, if all these other materials departments have moved on to the latest flash in the pan, why is everything still made out of metal? At least everything important. Everyone's heard the joke, right? Ceramics are the materials of tomorrow and will be for the foreseeable future. Why metals?
They can be used everywhere for the middle ground. In terms of ceramics and stiffness, overall fracture strength, and then polymers and their ductility. Metals are between them.
So you're going in the right direction there, right? I would say it's slightly more nuanced than it's the middle ground. Right? Yeah. Cheap and relatively cheap and tough. So there's two important things. But I would argue that even if metals were 10 times as expensive, we would still be using them. Toughness, yeah. So do you have another idea or do you want to expound on toughness?
I have another idea.
Okay, throw it out.
I was just going to say they're relatively easy to engineer to specific properties that you need.
I'll go with that, but it's not quite where I wanted to go. Because other materials can also be engineered in similar ways, but we still don't use them. Right? So, I'm sorry, what was your name? Josie. And I still don't know yours. Peter, Josie, and Sam. Okay. that's true. Again, I would probably argue that we can work around that if we absolutely needed to. All right. But let's come back to the idea of toughness. Why toughness? Relatively long lifespan. Right? Reliability. Okay. So you're again, that's hitting on the idea, right? We're almost there. Right, let's make it quick.
Can you shut the front window this picture?
Okay. Right, obviously we can label this as ceramic, polymer, and metal. Right? So what about the stress strain curve? Right. Where's toughness? So the area under the curve, right? Okay, so ceramic, very high strength, right? But not a huge amount of area. So if we do that, right, what units does this area have? Joules, right? It's energy. What's happening in the metal to give you a significantly larger area than this ceramic? Plastic deformation, right? We can dissipate a huge amount of energy before failure in metals by plastic deformation. Why is that important? Okay, that's another way of saying the same thing, but why is that important? We avoid catastrophic failure, right? Do you want a bridge that bends, or do you want a bridge that shatters? Right? Do you want a car that has crumple zones, right? Or do you want a car that crumbles to dust around you? Right? And so the other things that came up, cost, formability, machinability, these are all really important, right? Right? That's why engine blocks are made out of metal, right? Because you really don't, right? If someone could make a ceramic engine block cheaper, right? They would. There'd be no reason, right? We don't necessarily need the toughness, but for most applications, we do, right? Why is so much effort put into single crystal turbine blades, right? Nickel superalloys. They have an exceptionally high melting temperature, but there's tons of ceramics that could beat it, right? You wouldn't need any cooling, right? Because they'd never survive, right? You get a pebble in there and it bounces around, one tiny little piece of FOD and your whole engine just flies out the backside with the exhaust, and now you got a hollow tube. Right? So you can disagree with me, but my supposition is that the simple fact that metals can dissipate a significant degree of energy through plastic deformation before they fail. Right? Polymers would be ideal, but they don't have the strength we need. Right? So the area under that curve is pretty small. They don't have the strength to get there. Okay. So I mentioned earlier some basic rules of thumb. Oh, okay. This list is not by any means comprehensive. This is just what I threw together off the top of my head. That how I tend to think about metallurgical problems, right? And some basic guiding principles. And I said we use some pretty simple solid state physics with engineering intuition, right? It's one of my key parts of the definition of physical metallurgy. So what do I mean by that? Well, I have to think about something, right? It happens all the time. I collaborate with people like Professor Wang and Professor Zhao and Professor Fraser, who like phase transformations a lot. And so they're always giving me materials that have strange phase composition, strange phases, odd microstructures under odd service conditions, and ask me to do some simulation of their mechanical properties. So I have to start by understanding the material that they've plunked in front of me, the images that I'm looking at. And these are sort of the tools that I keep at hand to do so. Right? And I don't know who necessarily would come up with this exact same list as me. Now that I'm thinking about it, I could probably add a couple more things in there. I probably would have added Gibbs Thompson. If I thought about it for a little longer. But I was trying to explain to somebody, this is sort of the distillation of an entire undergraduate and graduate education in terms of material science, right? Leaving out the solid mechanics stuff. I'll have my own separate rules of thumb for those. But you could tack on a couple things like free volume for polymers and glasses, right? And then I would say this is all the important stuff in physical metallurgy in one fell swoop. And how I tend to see the world, right? So everyone, I think, as you go through the course, should be coming up with their own sets of rules of thumb, right? Of how they see the world, right? Have a couple key ideas that you internalize that you can use, right? And you notice a lot of these things are proportionalities, right? Meaning there's some constant outcome. It doesn't really matter. I just need to know what happens if I change something, what it's going to do. So what are these? So in terms of phase stability, are things going to form a single phase alloy, or are they going to phase separate? Right? Those are the Hume-Rothery rules, and we'll talk about those on the next slide and probably finish off on Friday. Right? So long-range diffusion, square root dt. Right? That should be a no-brainer for everybody. Right? Things that have to do with rates. Right? Also, the temperature dependence of mobility of the diffusivity is going to be an Arrhenius equation. Right? So understanding that temperature dependence tends to be Arrhenius, right? For some really good thermodynamics reasons that we won't go into right now, right? So the jump frequency, very important for growth rates. Right? The line energy of a dislocation. Right? Everyone should be able to pop off GB squared. Right? That should be something that you've learned in structure and defects and mechanical behavior. Right? Seen many, many times. Right? How does the stress field around the dislocation decay? 1 over the distance, right? And it's going to be proportional to the shear modulus of your material and the extent of the Berger's vector, right? Why the extent of the Berger's vector? Because that's how big your lattice distortion is. Right? Your shear modulus is going to tell you how it's going to be related to how big, how far out that effect spreads. Right? Poisson's ratio is in there too, but we can ignore it for now. Right? Hardening. The yield strength is going to be proportional to what? It's going to have a dependence on your dislocation density. That's work hardening. Right? Solid solution strengthening. Right? If I have a single phase alloy, right, my change in yield strength is going to be proportional to two things, like the square root of my concentration and the effective strain around the solute atom. Right? How big of a lattice distortion do they cause? Right? And so when I say simple physical pictures, that's sort of what I mean. Right? So when you have sort of exam questions, right, those are the key things. What's in this equation? What does it mean? It's more important than being able to spit out that exact equation. Right? When we get into precipitation strengthening, we see a lot of cutting and bowing. Right? But knowing what's in those two equations and what are the key physical ideas are really, really important. Yeah.
This shearing loop, like, is that equivalent to shearing and looping?
Shearing and looping through precipitates, right? So what's going to depend on is the distance between your particles, L, the radius of your particles, R, right? It's going to depend on them in different ways. And of course, cutting is also going to depend on the surface energy, right? Is your particle coherent or semi-coherent or incoherent, right? What's the energy of that? The energy of that. If you want to really get into it, it's going to depend on things like the antiphase boundary energy and other stuff, but those are sort of second order effects. What happens after the particles, the dislocations do it. And then Hall Petch. Right? If, I think I probably should have thrown Gibbs Thompson up there, right? That the curvature of a particle is going to affect its bulk free energy. Basically the same thing as capillarity. But any other suggestions as to what? Think back across your classes, phase transformations, and structure. Maybe Madelung energies for ordered phases. Right? Madelung constants. Right? Navarro. Oh, the Piles Navarro being there. Yeah, that probably would have been a useful one to throw up there. Any other ideas? So keep in mind, right? So again, this is how I see the world. Right? You might see it differently, but having a tool set on hand is probably the best thing you can do, and probably the most important, I would say, outcome of this. Okay, so into the actual meat. We'll spend a couple minutes on this and drop back on. So, anyone familiar with the Hume-Rothery? The concept of the Hume-Rothery rule? So where did you see them?
We talked about it
Okay, perfect, right? So it's a set again. It's a set of rules of thumb that were developed by William Hume-Rothery, Sir William Hume-Rothery, Fellow of the Royal Society. He is a fairly famous metallurgist at Oxford. My co-advisor, Roger Doherty, who's now retired, actually had him as a his PhD advisor. But he did a lot of really seminal work on the theory of alloys and development of a lot of aluminum and magnesium alloys here in Newport too. But he also came up with this set of rules for determining whether something is going to be form a solid solution or whether you're going to have some phase separation. And so he was totally deaf. He became when he was a young man, he had a virus infection that caused him to lose his hearing. So he was when he would go to conferences and meetings, he would hire undergraduate students to transcribe the talks for him. But of course, he, being stone deaf, had difficulty with volume control sometimes. And so there's a sort of legendary story of him at a conference, and one of the students was getting ready to write for him, and the speaker got up and was just about to start, and they hear Hume-Rothery from the back of the room say, "Don't bother, this one's not going to be worth listening to." So he's got two sets of rules, one for substitutional solid solutions, one for interstitial. And these are all pretty common sense once you think about them for a little bit, right? And the key ideas are that if you're going to actually make a solid solution over the whole range, right? It's got complete miscibility, right? That they should be about the same size, right? Important just for packing, right? That they should have the same crystal structure, right? Pretty basic ideas, right? So the solute and solvent should have similar electronegativities, right? Which is actually a very forward-thinking thing. When was the concept of electronegativity introduced? Right. Who introduced electronegativity? Famous guy won the Nobel Prize. And he sort of introduced it as a side note in his textbook. Right? Linus Pauling, ring a bell? Right? So he invented the whole idea of electronegativity in the 50s. Right? So why is it that the solute and the solvent, right, or the matrix and the alloying elements, the primary metal and the alloying elements, why should they have similar electronegativity? What would happen if they had very different electronegativity? What's that? Intermetallic secondary phase, right? So high electronegativity for bonding gives you what kind of bonds? Ionic bonds, right? So intermetallics with a high ionic character are going to tend to be very, very brittle. Right? Okay, and then the complicated one, right? So you want the same valency. Right? What the heck does that mean? You have a similar, right? Similar numbers of electrons, right, floating around. Why Why is that important? Yeah. So what does metallic bonding look like? We've got a bunch of delocalized electrons, right? What happens if you introduce atoms with a lot more or a lot fewer of these delocalized bonding electrons, right? It's going to cause regions of slightly charge imbalance, right? And so this is the electronic stabilization of the crystal structure, right? Technically, if anyone is doing electronic properties, or someone is in Professor Ghazi Saeedi's or Professor Wendell's group, we could talk about the Fermi surface as a sphere and intercepts the Brion zone, and we can get into all that nonsense. But it's not really super important for this class, but it is important to understand that the electronic structure can have a very important role in stabilizing different compounds. So this is the copper-zinc phase diagram, right? So what's copper? What crystal structure is copper? FCC. What about zinc? HCP. So by the basic rule, should there be any really significant miscibility in the rules of thumb, any significant miscibility between copper and zinc? Not really, but even at room temperature, you can develop 35% zinc and copper, right? And then you get these islands of stability. Okay, so now we've got a miscibility gap, but now I've got a stable phase here, stable single phase. I've got a stable single phase here, another miscibility gap, stable single phase here, another miscibility gap, right? So these stable phases where you would ordinarily not expect to make a solid solution, these are called Hume-Rothery phases, right? Where you get these lines of these separated by miscibility gaps. And this is completely due to the electronic structure at that point, stabilizing. So your FCC at this end, HCP at this end, and then honestly, get off the top of my head. We'll talk about more about this when we hit brasses. But we will stop there for today. We'll briefly pick up with intermetallics. I mean, not intermetallics, interstitials on Friday. There will be a quiz Friday. And Linda, right? Not yet. The notes will definitely be posted online before the lecture. Did everyone not get the email, the message I sent from Canvas? What's that? Is that no or yes? So some did, some didn't. Okay, I will have to figure out why only part of the class got the message. But yes, the notes will be posted. The notes for Friday and Monday will be posted tonight or tomorrow morning at the latest. And so generally the notes will be up a couple days before time. And the Friday quiz will be at the beginning of the class. And because it only covers what was today, there's not exactly a lot of material that I could ask, right? So there's really only 3 possible questions that I could ask.
Did everyone sign the sheet?
Yeah, anyone who did not sign, this first week is super important for attendance because I have to report anyone who doesn't show up the first week for financial aid. Sure, hold on just one quick second. I want to make sure that I get